This video is about visual representations of multiplication. So just like we did with addition and subtraction, we're talking about drawings that help us understand multiplication. Well, multiplication is repeated addition, so all of the models we used for addition also work for multiplication. So we're going to do a couple of examples of the length and the number line. So if we have something like 4 times 9, thinking of it as repeated addition, that's 4 added together 9 times. So if you remember with our number line model, every number gets represented by an arrow, and the length of the arrow determines the value. So in this case, each green arrow has a length of 4, and then I'm going to add 9 of them. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 4 arrows. So in other words, 4 added 9 times, I end up at 36. So 9 times 4 is 36. Or we can think of this the other way. This could be 9 added together 4 times. And this time I would have these purple arrows, each one being a length of 9. So then I would add 1, 2, 3, 4 of those. And you notice that you still end up at the same place. You still end up at 36. You can also use number line model with decimals and fractions, as we did with adding and subtracting. You just need to make sure that you label the number line appropriately. Okay, more effective for us, and I think in my opinion, is the area model for multiplication. And the reason I say that is because the length model sometimes gets a little bit messy if, let's say, I'm multiplying 2.5 times 3.5. So now I have an arrow that's 3.5 long, but then I need to take half of that. And so that gets a little bit more confusing, and that's where area can be super, super helpful. So we're going to start with small whole numbers, and then we're going to build up to the ones that are a little bit more complicated. So you probably don't need an area model to do 5 times 6, but it's just going to get us started. So let's think about blocks. So 5 times 6 is 5 added together 6 times. So here I have a group of 5 blocks, and I have 6 of those. So I have 6 groups of 5 blocks. And if I count that up, I can see that there are 30 blocks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30 blocks. So I know that if I take a group of 5 6 times, then I end up with 30. So let's push all those blocks together. So now they make a nice compact rectangle, and they look something more like this. Now let's think about where the 5 and the 6 and the 30 are. So the 5 is one length, or the length of one side. So this has a length of 5, right? 1, 2, 3, 4, 5. 6 is going to show up here. This is a length of 6. 1, 2, 3, 4, 5, 6. So there's 6. And the 30 is the area of that rectangle. So the 30 is now inside of that rectangle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30. So we're going to exploit this idea, right? That the length of one side times the length of the other side gives you the area of the rectangle, which is, again, something you're probably comfortable with, finding the area of a rectangle. So multiplication is the area of the rectangle that those two numbers create. So let's just do it for 12 times 7, just so you can see it. So this is 12 added together 7 times. So here is a 12, another 12, another 12, and there's 7 of them. So now I have 7 times 12. So to find the answer, then I need to find the area of this. So this is a little bit tedious, but we can just count. So it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, etc., etc. I just count all those squares, and it turns out that the area is 84. There are 84 boxes. So 12 times 7 is 84. 12 times 7 is 84. Now here's where it's really helpful in my opinion. So again, I love to draw my fractions. You know that. I'm obsessed with drawing my fractions. And this is one of those cases where it again is super helpful to draw. So I have a half times 3/4. So this could be interpreted as a half of 3/4. So we're going to start with 3/4. So a half of 3/4 means find 3/4 and then take half of that. So I drew a square that represented 1 and drew the 3/4 on the inside. I didn't just draw 3 little boxes and shade them all in, because then I would get confused on what they were. I want my picture to show the 3/4. And then I want half of that shaded region. So I'm just going to take that shaded region and literally cut it in half. So if my original lines were vertical, then my half line is going to go horizontal. And then I'm going to take half of the shaded area. So half of the bright green, the original 3/4, would be this darker green. And so now I can describe that by saying, that's 1, 2, 3 parts when there are 1, 2, 3, 4, 5, 6, 7, 8 parts in the whole. So half of 3/4 is 3/8. And we can also think of this the other way. So a half times 3/4 could mean 3/4 of 1/2. So let's start with 1/2. So I drew 1/2. I drew a box, I cut it in half, and I shaded it red. Now, I want 3/4 of that shaded part. So I'm going to cut it into 4 equal parts and take 3 of them. Again, to describe my answer then, I have 1, 2, 3 parts. There are 1, 2, 3, 4, 5, 6, 7, 8 parts in the whole. So again, I have 3/8. So let's try this again. 2/3 times 3/8. So pause this video, draw it out, and see what you get. 2/3 times 3/8. Okay, there are 2 ways to interpret it. You probably interpreted one or the other. So I'm going to start with 3/8 of 2/3. In other words, I'm starting with 2/3 and I'm taking 3/8 of that shaded area. So here's my 2/3. I drew 2/3, shaded it in turquoise, and then I want to split the shaded area into 8 equal parts. So I'm going to go 8 equal parts in the horizontal direction and take 3 of those. So here are my 8 equal parts. Okay, my 8 equal parts are going in this direction. That's 1, that's 2, 3, 4, 5, 6, 7, 8. Those are my 8 equal parts. And then because it's 3/8, I want 3 of them. So I'm taking these 3 up here. So if I look at the dark shaded, there are 1, 2, 3, 4, 5, 6 of those dark shaded blocks, and then if I count the whole, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I have 6/24. Now, this number can be reduced, and if you reduce it, fine. If you don't, fine. Okay, maybe you interpreted this the other way. So 2/3 of 3/8. So this time we're going to start with the 3/8, and then we're going to split that into thirds and take 2 of them. So I did the 8ths up and down. Okay, so if I look here, this is my 1, 2, 3/8. 1, 2, 3, 4, 5 to give me a total of 8 pieces. I shaded 3 of them. Then of that, I wanted 2/3. So I split it into thirds going in this direction. Here's my 1, 2, 3. And I only wanted 2 of those. Okay, so I ended up with the brown, the dark brown, as my solution. So I have 1, 2, 3, 4, 5, 6 pieces when there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 pieces in the hole. So again, I got 6 24ths. Okay, mixed numbers. So now our drawing is going to get a little bit bigger, but it's exactly the same idea. So 1 2/3 times 2 3/4. So this is 1 2/3 added 2 3/4 times. That's going to take some getting used to. 1 2/3 added 2 3/4 times. So I'm going to start by just drawing 1 2/3. So when I start doing mixed numbers, I'm going to need to distinguish what is a whole versus what is breaking a whole up. So what I mean by that is my bold lines are representing 1. So this rectangle here, that has an area of 1. The rectangle right below it, that's another rectangle that has an area of 1. And the reason that I did that is so that I could show 1 and 2/3. So now the skinny lines are the ones that are going to help me break up the whole. The thick lines represent the whole. Okay, getting back to where we were. 1 2/3 added 2 3/4 times. So here's 1 2/3 one time. Here's 1 2/3 again. So that's 1 2/3 2 times. So now I need the 3/4. So I have the 1 2/3, and then I broke it up into 4 equal parts going down, and I shaded 3 of those equal parts. This part's going to take a little bit of practice, so bear with me. You got to try these a few times. So we started by drawing 1 2/3, and then we took 3/4 of that shaded region. So now I have a rectangle that looks like this. So here is 1 2/3. So if you notice, that's actually this length, 1 2/3, times 2 3/4. 1, 2, 3/4. So there's my 1 2/3 and then 2 3/4. And the solution, the answer, is the area of that purple rectangle. So that's our next task. How do we figure out what the area of that purple rectangle is? One way to do it is to think about moving pieces. So here's what I mean by that. I'm going to grab this piece right here. And I know that that piece fits perfectly right here. So I'm going to move it right over here and get rid of this one. And then I'm going to come up here and I'm going to grab this piece. And I know that that piece fits perfectly here. So I'm going to go ahead and put that there. Okay, and I'm going to get rid of that piece. So now I have something that looks like this. Now, I no longer have a rectangle, but that's okay with me. All I'm trying to figure out is the area of this shaded part. So right now, so far, I know that it's 1, 2, 3. And then I got to deal with these sort of smaller ones over here. So I'm actually going to do some more moving. I know that this little one right here fits down here. So I'm going to shade that in. And this little one here fits here. So I'm going to shade that in. And the reason that that is helpful is now I have another hole. I have a 4. So now I've moved my little blocks. So I still have 1, 2, 3. I have 4 holes. Okay, those, again, the bold, the thick black lines represent a hole. So I have 4 of those filled in, and now I just have to describe this last piece. Well, that's not too bad, Because it's broken up into equal size pieces. So now I have 1, 2, 3, 4, 5, 6, 7 pieces when there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces in the whole. So I end up with 4 and 7/12. Now, going back to the original rectangle before I moved it all around, another way to count up this area is to just break all of the pieces into the same size little pieces. Okay, so in other words, if I just glance at this, okay, I know that this piece right here is not the same size as this piece right here. So usually what you do is you just look for the smallest piece. So the smallest piece seems to be the ones that are over here. And these are broken into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12ths. So then let's come over to all of these pieces and all of these pieces and break those into 12ths. Usually, this is pretty straightforward. This has been split into 3 in this direction and 4 in this direction. These have already been split into 3 in the horizontal direction, so I just need to come back and split it into 4 in the vertical direction. So cleaning that up a little bit, it looks like this. Now I just have a bunch of 12ths, and now I just count them. It's kind of a lot to count, but you just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, etc., etc. I count up all those boxes. It turns out I have 55 boxes. So I have 55 pieces when there are 12 pieces in a whole. Remember, the bold lines are showing you a whole. There are only 12 pieces inside of each hole. So it's important that you remember that it is 55/12. You can then, from there, turn that into a mixed number if you want. I am totally fine with 55/12. Okay, areas with decimals. Areas can be extremely helpful with decimals as well, as long as the decimals don't get too long. In other words, if they're wholes and tenths, then you're okay. If you have numbers that are wholes and tenths and hundredths and thousands and 10,000s, it's possible, but it's really, really hard and tedious and difficult to draw those kinds of drawings. So, an example of 1 and 4/10 times 3 and 2/10. So here is 1 and 4/10. So again, the bold rectangles represent 1, and then the skinny lines, those are breaking it into tenths. So this is my 1, and this is my 4/10. Right? I shaded 4. There are 10 pieces in that lower rectangle. But I need this 3 and 2/10 times. So here's my 1 and 4/10 once. Here it is 2 times, 3 times, and then 2/10 of a time. So notice what I did was I took my 1 and 4/10, which was actually this big, and I broke it up into 10 equal parts going vertically. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I took 2 of those parts. So now if I want to count up this rectangle, it's kind of nice. The large rectangle, the bold is what I mean by the large one. The bold ones have an area of 1. So this is 1, this is 2, and this is 3. Okay, so those are what I'm calling my large rectangles. And then the long, skinny rectangles, they're a tenth. So that's these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's those. And then the small rectangles, which are pretty small in my picture, those are my hundredths. So that's these. The 1, 2, can't see that color. Let's try a different one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28. So those 28 ones, sorry, those dots didn't quite all get in there, but hopefully you got the right idea. So the drawings are nice for fractions in that they kind of will end up mirroring our 10 by 10 grids, right? So the big rectangle is 1, and then a row or a column is a tenth, and then the little squares are hundredths. So if I go to add this up, so this is what I just counted up for you. There were 3 ones, 12 tenths, and 28 hundredths. So I need to go ahead and add those together. I end up with 4 and 48 hundredths. So I had to do a little carrying in there, or if you want to think about it as moving the pieces around like we did on the other one, you'll still end up with the 4 and 48 hundredths. So in summary, areas of rectangles can be used to evaluate multiplication computations. Particularly helpful with fractions.